Hello, welcome to everybody. My name is Davide Spriano, and this is the introductory lecture for my talk. And this is going to be about Katzir spaces and Katzir cube complexes. What I'm going to talk about are the definition of those two classes. And then to the end, I'm going to talk about something called the contact graph and some generalization by Anthony Genois, which then will be the background for the research part of the talk. So if you know what a Katzir space is or a Katzir cube complex is, just essentially skip this part and go to the next one. Okay, right. So we want to talk about Katzir spaces. And well, what is the idea? The idea is that we want to encode the notion of curvature in a general metric space. So we all studied some version of Riemannian geometry, some sort of course of it, maybe geometry 1, geometry 2. And there is the notion of sectional curvature, etc. But if you just have a general metric space, how do you define curvature? Just using the metric. And the idea is the following. The idea is that triangles are no fatter than in Euclidean 2 space. So let me give you an actual definition. Let's take a metric space XD that is geodesic, meaning that for any 2 points there exists a shortest path between them, a geodetic. Then we say that it is Katzir if whenever we have a geodesic triangle, i.e. a collection of 3 geodesic connecting x, y, y, z, z, and we have point P and Q on the triangle, then we have the following thing, that if we take the triangle in X, then we can take a comparison triangle in the Euclidean 2 space. That is to say, we take the distance between X and Y, this is a number, the Y and Z is also a number, XZ is a number, and those numbers satisfy the triangular inequality. So there should be a triangle in Euclidean 2 space with the same side lengths, and then we look at the distance between XP and XQ, and similarly, we find points P bar and Q bar, and now we compare the two distances, and we want that the distance in X between P and Q is smaller or equal than the distance in Euclidean 2 space between P bar and Q bar. In some sense, the triangle is thinner, it's less thick. Okay, and this notion is very simple, but it's really good, and it has a lot of good consequences. So let me give you some facts and with some proofs. So the first thing is that Katzir spaces are uniquely geodesic. So between any 2 points, we don't just have that they exist a geodesic, but they exist a unique one. So here is the proof. So I have X and I have Y, which are 2 points in my Katzir space, and suppose that we have 2 different geodesics, alpha and beta. Well, now let's consider the triangle with sides alpha, beta, and just y. So the constant geodesic on 1 point. So when we look at the comparison triangle in Euclidean space, this would just be, we would have x bar, y bar, and this is going to be alpha bar equal beta bar. That is to say, those 2 sides get collapsed. So now any 2 points that would be on alpha and beta needs to be mapped to the same point. And since distance in Euclidean space are bigger, those 2 points would actually need to be at distance 0, so identified. Okay, so Katzir spaces are uniquely geodesic. Nice, this is a nice property. And let me tell you another one, which is that if I now take a geodesic gamma, there exists a well-defined closest point projection from the whole space to gamma. So that is to say that if I take now any point, I take gamma, which is maybe this geodesic, and I take any point X, there exists a unique point in gamma that is closest to X. Okay, so here is the proof. Suppose this was not the case. Suppose that we had 2 points, Y and Y prime, that were both closest to X, and they were not the same. So the distance between Y and Y prime, this distance is some epsilon bigger than 0. Well, then again, we have one trick. Let's use it. So let's go to Euclidean 2 space and take a comparison triangle. Well, this is going to be an isosceles triangle with x bar, y bar, and y bar prime. And there needs to be a point P such that the distance between X bar and P, let's call it P bar, is smaller than the distance between X bar and Y bar, or X bar and Y bar prime. So if I take the corresponding point P here, again, we have that the distance between X and P was smaller than the distance between X and Y, or X and Y prime, contradicting them to be closest point projection. Okay, so closest point projection are unique. And those two facts are really quite useful, and they follow very simply from just a definition. Let me tell you a couple of other interesting facts. The first one is that the closest point projection is distance then increasing, meaning that if I have 2 points X and Y, then the distance between X and Y is bigger or equal the distance between pi gamma of X and pi gamma of Y. This is exactly the same as saying that the projection is 1 Lipschitz. And then the distance is convex along constant speed geodesic. So what does it mean? It means that if I have alpha and beta, and those are geodesic, that call it gamma, well, that are parameterized from 0, 1 to X, and from 0, 1 to X, then the function that assigned to T assigns the distance between gamma of T and beta of T. This is convex. So this is a function from R to R, and this is a convex function. And then as a consequence, this has a very nice consequence, because we take any point, and now let's call it O, and then to any other point of your Cat0 space, just connect it to a geodesic. And what happens is that if you now just slide down this point linearly, we can contract all the space to a point. And it is important that the distance is convex. It makes such that this contraction map is really a continuous map, it's really an homotopy, but that is to say Cat0 spaces are contractible. Right, and this is our first source of, now we're going to look at some examples, non-examples. So non-examples are any space that is not contractible, is not a Cat0 space. Well, so think about any graph or any space that has any topology is not Cat0 essentially. And so what are examples? Well, the base example is Rn with the Euclidean matrix, so Euclidean space, Hn with the standard hyperbolic matrix, and actually those are both examples of any complete Riemannian manifold of non-positive sectional curvature. Right, all of those will form Cat0 spaces, and also trees. If we take a graph without cycles, is also going to be a Cat0 space. Okay, so now let me make a remark about the difference between Cat0 and hyperbolic spaces. Well, so if we just talk about spaces, those two classes don't really talk to each other. So Cat0 spaces and Gromov hyperbolic spaces have some intersections, such as trees and hyperbolic 2 spaces, but there are examples of each that do not belong to the other one. So Euclidean 2 space is not hyperbolic, as we know, and any space that is not contractible and hyperbolic, for instance, non-tree Cayley graphs of some groups, would not be Gromov hyperbolic spaces. Okay, but in some sense, when you look at the definition, they are both using triangles, and Cat0 seems in some sense like a slightly weaker condition because it doesn't require the triangle to be very thin, just less, just as thin as the Euclidean one. But all of these starts not working in fine dimensions. And what if we kind of not consider the fine geometry? And so, for instance, what if we just think about groups? And let me just remind you very quickly. So a group G is Cat0 respectively hyperbolic if it acts geometrically on a Cat0 respectively hyperbolic space. Well, and now in this setting, it is not known if every hyperbolic group is a Cat0 group. That is to say, it is unknown if there exists a hyperbolic group that cannot act geometrically on a Cat0 space. So you have a hyperbolic group, maybe you don't know you don't have any obvious Cat0 space with every X, but maybe you can smooth somehow its Cayley graph to make it contractible and satisfy the Cat0 space. This is one of the big open questions in the field, and I think it's very basic and interesting to know about. Okay, so now let me talk about Kadziya cube complexes. The Kadziya cube complexes form a subclass of Kadziya spaces, but we will not really think about them as a subclass, but rather space with their own interesting property, because most of the interesting property and proofs actually about Kadziya cube complexes really use the cube complex structure rather than the Kadziya structure. But I'm getting ahead of myself. Let me define them. So a Kadziya cube complex is obtained as follows. You need to glue cubes. So a cube, I think of the product of the interval 0, 1 in Euclidean space along faces via surjective isometry. So faces need to go to faces in an isometric and surjective method. So in particular, I cannot glue a vertex into the interior of a face because that would not be a surjection. I would need to cover the whole face. It needs to be an isometry, so things like that, of course, cannot work. And they want the resulting space to be simply connected. And they want a technical condition that says that links are flagged. I will not explain this. This is not very hard. Yes, it's just some combinatorial condition that is easy to check. So let me give you an example. So this is how a Kadziya cube complex look like. There are some cubes, 1 dimension, 2 dimension, and 3 dimensional cubes or more that are all glued together. And what really makes Kadziya cube complex interesting and differentiates them is that they have something called hyperplanes, which will provide a rich combinatorial structure that allows a lot of interesting proofs. And what is a hyperplane? Well, intuitively, we first need the notion of a mid-cube. What is a mid-cube? We just take a Euclidean cube, which we know what it is, and we restrict one of the coordinates to 1/2. So we have as many mid-cubes as the dimension. So here we would have these mid-cube over here, the orange one, or the red one, which does like that, or the blue one. So we have 3 mid-cubes, essentially one in which for each coordinate we restrict. And then we want to propagate them. Okay, so let me explain this in a picture that is easy. This is a picture with some mid-cube that can be propagated. But then if I take, for instance, this other mid-cube, like this red one over here, I see that it touches another mid-cube on a cube next to it, like adjacent to it. And so I can start propagating and propagating. And whenever I'm touching another mid-cube, I just add that mid-cube to the hyperplane. So I go like these, etc. And there are those 2 blue examples are other 2 hyperplanes. And also all the one on the previous picture, they are all hyperplanes. They just did not propagate. Right, and hyperplanes are great, and they're really useful to understand the geometry of a space. And let me tell you some properties of hyperplanes. The first one is that hyperplanes are convex. I did not define what convex is. Essentially, every reasonable notion of convexity you can have, hyperplanes would be convex with respect to that notion. And the other one is that they cut the space into 2 components. So you somehow have those walls that are very well behaved. They really cut the space in 2 and are convex. And here is perhaps not the most useful fact of hyperplanes, but it's going to be very useful for us, and it's quite neat, is the following, that if I now take the combinatorial distance between 2 vertices, so what does this mean? This is just the distance in the one skeleton. In one skeleton. So we just look at the graph which is made by the one skeleton, and we look at the distance in that graph between 2 vertices, x and y. This is the size of the maximal collection of hyperplanes separating x from y. And this phrasing is a bit weird. There is a reason why I'm phrasing this way. It's really just, well, maximal collection is the weird part. It's just all hyperplanes that separate x from y. I just take all of them. And this is a count, and this is going to give me the distance. So let's take an example. I have here x and here y. And then the point is that if I take any geodesic between the 2 of them, well, every hyperplane that separates x and y needs to cross the geodesic. And since hyperplanes, when you go on an edge, each edge is intersected by exactly 1 hyperplane, I can intersect at most, I intersect 1 hyperplane for each edge. And since they are convex, I can intersect every hyperplane once. So this is why I get this identification. Okay, so we have Kadzier cube complexes, which is this class of cube complexes, which sometimes has this different metric, which we just look at the one skeleton, which by the way is quite isometric to the Kadzier metric, which is the metric considered by taking the Euclidean metric in each cube. So taking one or taking the other is a bit of a matter of taste, but really the combinatorial one, it uses hyperplane and is so much easier to deal with in practice. And now that I introduced those two classes, let me start getting at what I want to get, which is, okay, so we have these classes, what do we want to do? And what we want to do is we want to extract hyperbolicity from those classes. So we want to have, and now let me talk about Kadzier complexes first, because they are easier. We want to have some sort of procedure that, given a cube complex, it looks at it, sees only the hyperbolic bits, and the non-hyperbolic bits discards them. And this is given by the contact graphs. So those were the contact graph actually is only one of them, and it was introduced by Hagen, and then Genoa took this construction and realized it could be generalized and made a whole family of contact graphs. And this is a procedure that where you take the input is your Kadzier cube complex, and then the output is going to be a hyperbolic space, which is exactly what we were talking about. But there is a very important thing to keep track of, that if we have a group action on a Kadzier cube complex, then we will still act on this hyperbolic space. Okay, and the hyperbolic space is obtained from the cube complex. So for instance, if we were acting transitively on the vertices, then we would also act transitively on the vertices of the hyperbolic space. And before I explain the procedure, just to tell you some ideas, the idea is that there is some threshold that we need in this procedure, and this is why we get contact graphs. We get many graphs by changing the threshold. And the idea is that as we increase the threshold, we are allowing to consider less hyperbolic regions, so regions that are still hyperbolic, but maybe not so much. And as a consequence, our output will be a less hyperbolic space. So as we increase our threshold, we will see more of the space, but we will get, as a result, a space that in general is less hyperbolic. So I just, to put this on the board again, we see the distance between two vertices in the one skeleton is the size of the maximal collection of hyperplanes separating x from y. And the new distance we need to define, which has this threshold L embedded in it, is the L distance between x and y to be the size of the maximal L separated collection of hyperplanes separating x from y. And what does L separated means? I said that a collection H1, Hn form an L separated collection if H1 and Hn are disjoint. Okay, so this is the first difference. We're just considering collection of these joint hyperplanes, whereas here was just in any collection, just as long as it's separated. And then this is the most technical condition. Whenever I take H1, Hi, and Hj in my collection, there exist at most L other hyperplanes that intersect both. Let's see. So the picture is I have two hyperplanes in my collection, and I can only find L that intersect both. Let's see these in a picture. Let's look at this Kadzier cube complex is just a strip, and let's take 2 points, x and y. So if I take a D0, so where my threshold is L, so L is a very strong threshold between x and y, I say, well, how many zero separated hyperplanes I can fit between x and y? So how many hyperplanes can I put between x and y such that there is no other hyperplanes plane that intersect any element in this collection? And the answer is essentially 1. Well, any that you put, I can put, because being separated makes sense. So this is a condition on a collection. So if I have only one hyperplane, there is essentially nothing to check because it is disjoint from itself, and for any pair, this condition is just empty. So any old hyperplane I want to pick would just work. I could pick the vertical one or this horizontal one, but as long as I have two, try to fit a second one. For instance, let's say I have two disjoint ones. Let's say I was going to pick those two green ones, then they would not be zero separated anymore, because there exists one other hyperplane that intersects both. The distance, the zero distance between x and y is 1. However, if I take the 1 distance between x and y, is 15, which is essentially the original distance, because I can fit all of those green hyperplanes, and now those would be a disjoint family, and there exists at most one hyperplanes that intersect any two of them, which is the red one. Okay. Right. And so what is how does the resulting space look like? So if I take x, let's say that x is the name of the cube complex, if I give it the zero distance, this is going to be just a complete graph where every two vertices have distance 1. But if I give it the 1 distance, it's going to be this sort of quasi-line. And this, you see, is going to be quasi-symmetric to the other graph. So in one situation, in both cases, we are recovering a hyperbolic space. A point is a hyperbolic space, and the line is a hyperbolic space. But in the second condition, we are getting more information about the space because we are increasing the threshold. And now, if you would imagine like larger and larger strips, you could just make the same example for higher thresholds. But as you do, you will see your resulting space will be less and less hyperbolic. So that is what I meant with you increase the threshold, you see more, but you get a less hyperbolic result. Let me just show you another example to conclude, which is the trio flat. The trio flat is the universal cover of a torus wedge circle, which can be made naturally in a Katsir cube complex as is in the picture. So you have all of those flats, those are infinite flats, and then each point, each of those like integer lattice somehow in those lifts of the torus. To each of these are attached two edges, which are the lift of the circle, and all of these is arranged in a tree, like fashion. And the point is that if I am trying to form an L-separated collection, I can always only put at most one hyperplane per flat, because as soon as I put two disjoint hyperplanes in the same flat, let's say I'm putting those two, there are infinitely many, which will be the red ones, hyperplane that intersect both. So in each flat, I can stick only one hyperplane. So if I now try to separate 2 points, well, the distance, the L distance between those 2 points, essentially will count 1 for each of those vertical edges I need to go. Let's say the point, 1 point is here, x, and 1 point is here, y. My L distance will count 1 for each of those vertical lines, but will count 1 for each flat. So essentially, the space you will be obtaining is the trio flat where all the flats get collapsed to bounded set, which is so an infinite variant tree, and is going to be exactly in this particular case is going to be the Basser tree for this grid, for the fundamental grid of this complex. Okay, so in this example, we also can extract. This is a more interesting space where we can extract the hyperbolicity. Okay, and thank you for listening. And in the next talk, I will take this, which is going to be based on joint work with Harry Petit and Abdul Zaloom. I will take this sort of concept and try to generalize to general Katsira spaces without a combinatorial structure, and hopefully obtain some results.